Hello, we continue learning physical methods of investigation, and today we are going to talk about nuclear magnetic resonance. This is a kind of more complicated topic, but I will try to do my best to explain to you the essence of this method by using kind of simpler words. Here we go. Okay. In electromagnetism, magnetic field is a physical property of space that quantifies the magnetic strength at a given location. The point is the magnetic strength is one of the indicators that we can rely on to determine the NMR spectrum. We will talk about this. The magnetic field deflects moving electric charges, including electric currents, apply torques on magnets to twist them in the direction of the magnetic field and attract or repel magnets and magnetic materials such as iron. So magnetic field affects the nucleus as well, because nucleus has its own magnetic field. The magnetic field of the nucleus is affected by the external magnet. This is the point that we can use to determine the NMR spectrum of compounds. In addition, a time-varying magnetic field induces electric currents. Here we can see that this is one of the types of external magnets which show us the direction south and north. So based on this, we can understand the existence of the magnetic field. So that magnetic field affects the nucleus of compounds as well. NMR spectroscopy tool looks like this. It is very big, and how inside of the tool looks like is given at the end of the lesson. So for now, what we can understand is this is a kind of big tool, an expensive tool. And how do we determine the structure of a molecule without destroying it? Can be explained by using by the NMR spectroscopy. It is a spectroscopic technique based on interaction between nuclear spins and magnetic field. We will talk about nuclear spins, and we know about magnetic field. So the key ideas here in this spectroscopy is the interaction between the magnetic field and nuclear spins. Based on the interaction between nuclear spins and magnetic field, we can detect the response of the nuclear magnetic field to radio frequency radiation. This method is widely used in drug discovery, metabolomics, and environmental sciences. I would say in all disciplines of natural sciences. And in the term NMR, we have resonance. Let's remember what resonance is. Resonance is the physical phenomenon when an object or system vibrates with significantly increased amplitude when subjected to an external force or wave that matches its own natural frequency. So the point is in increased amplitude. That increased amplitude helps us to find out the signals that belongs to different atoms. Based on that, those signals that are specific to different atoms, we can find out about their belongings. So then we can find out different functional groups that makes up the compounds. So the increased amplitude is the point that determines the NMR spectroscopy. It commonly describes amplified sound. The resonance is commonly described describes amplified sound, mechanical vibrations, and electrical signal. And metaphorically, it means a lasting impact or the personal connection. In our case, the resonance belongs to the increased amplitude. Okay. Magnetic field. Here, let's compare and find out about the differences between the electric field and the magnetic field. We know that the source of the electric field are the charges, but the point that the charges make the charges that are expected not moving make the electric field, but the moving charges make the magnets. No magnetic field is produced by stationary charges. This the stationary charges mean that the electrons, for example, have their own spin, they have their own speed, but when electrons turn to their excited state, so in their excited states, they can affect neighboring electrons, so that causes the electricity, and around the electricity, we can see this kind of magnetic field. This is the difference that electric field does not have this kind of magnetic, let's say, field, but ma magnetic field its own source. I mean, the moving charges have this kind of magnetic field. Okay. uh, Not in their stationary state, but in their excited state, let's say. So electric field acts on all charges moving or at rest, plus or minus, and magnetic field acts on only moving charges, no force on charge at rest. So this is another difference between them. And the force direction in the electric field, okay, can be described like this. And anyway, I mean, and the direction of the magnetic field can be determined by the rule of left hand, termed left hand rule. So if the electricity is moving upstairs, for example, yeah, in this direction, so the magnetic field has this kind of circle. If the electricity is flowing from the left to the right, so then we can make a conclusion that the direction of the circle is something like that. Yeah, this side. If it's upside, so the circle has this kind of direction. Okay, I hope you understand my point of view. And we can see the electric field effect around the balloon attracting paper bits, yeah? And we see the presence of the magnetic field by using this kind of tools that helps us to determine the north and south. Okay, together electric field and magnetic field make electromagnetic field, and we learned about electromagnetic waves that include the sunlight, radio waves, microwaves, yeah, and gamma rays, X-rays, etc. So the point that we have to understand is that the magnetic field that is formed around the acting charged particles uh, affect the magnetic field of the nucleus, and there we can observe the resonance. Based on that resonance, we can identify the protons or carbon-13 isotopes that belong to different functional groups. Okay, spin is the important point that we have to understand. If the magnetic field has, let's say, north and south location like this, so the spin might have this kind of, let's say, spin. Yeah? A spinning charge generates a magnetic field as shown by the animation on the right. Yeah? The resulting spin magnet has a magnetic moment, yeah, proportional to the spin. And in the presence of the external field, as indicated here, B0, yeah, two spin states can exist, plus 1 over 2 or minus 1 over 2. Plus 1 over 2 or alpha spin is the spin that has low energy. and minus 1/2 or beta spin is the spin that has higher energy. This is the point. The magnetic moment of the lower energy plus 1/2 state is aligned with the external field as indicated here. Yeah, and but that of the higher energy is indicated here. Uh, that has the energy minus 1/2 spin state is opposite to the external field. Note that they are representing the external field, the north. Okay, and this is another example where we can understand that different atoms have their magnetic field in their nuclei that have different directions, changing around the magnetic, let's say, momentum, yeah, and spin, of course, based on that. But under the effect of the applied magnetic field, we can observe this kind of, let's say, spins. Yeah, the ones with lower energy are to be aligned with the external magnetic field, and the ones with the higher energy written with minus 1/2 spin are aligned against the applied magnetic field. These are the points that can explain the resonance and the NMR's spectroscopy. An atomic nucleus that has an odd mass number or an odd atomic number has a nuclear spin and behaves as a magnet in an external magnetic field, like, for example, hydrogen 1 or carbon 13 have nuclear spin, but not the carbon 12. Here we can understand about this more. If the number of protons is an even number and the number of neutrons is an even number, so their mass number is even and their nuclear spin equals 0. And they are expected to be, they are not expected, okay, they are not NMR active. Okay, but if the protons number is odd and neutrons number is odd, so then they are NMR active. If the neutrons number odd or even, but let's say without the neutrons, so they are also can be active. Here we can understand this thing is carbon 12 or oxygen 16 isotopes, for example, are NMR inactive. They are not NMR active because here, as we talked, that the protons number is 6 in carbon 12 and the neutrons number is 6. So they are, I mean, this isotope is NMR inactive. Likewise, oxygen 16 isotope has 8 protons and 8 neutrons. So it is also NMR inactive. But hydrogen 1 protein or carbon 13 isotope or fluorine 19 isotope, phosphorus 31 or nitrogen 15 isotopes are NMR active due to their odd numbers in their nuclei. I have to add here one more thing that nitrogen 14 is also NMR active, as indicated here, because it has odd number of protons and odd number of neutrons in its nuclei. Okay, so that E does not, I mean, this item, let's say capital E, does not equal 0. If it equals 0, those atoms like carbon 12 and oxygen 16 are NMR inactive. If E does not equal 1, does not equal 0, so they are NMR active. Here we can understand more about them. Even and even numbers are not in NMR active. They do not produce NMR signals, and odd numbers always gives NMR signals because capital I does not equal 0. Here we can see that protein produces strongest signals. Carbon-13 produces signals as well, but in the nature it is low abundant. Carbon-13 isotope makes 1.1% of the carbon in the nature. Fluorine-19 is also very sensitive. Phosphorus-31 also produce signals, and it is important in biochemistry. Deuterium, it has 1 and 1 protons and neutrons number. It is used as solvent. Does it produce signals? Yes, it does, but they are not strong signals. That is why its signals can be excluded, and therefore it's used as the solvent. Deuterated water is used to dissolve some compounds that have hydrophilic nature, or deuterated chloroform is used to dissolve the compounds that are more hydrophobic. And nitrogen 14 has a quadruple nucleus, and it produces signals of broad, let's say, peak. Next. In this video now we are going to watch nuclear magnetic resonance, so then we can understand how the process is carried out more. Nuclear magnetic resonance. The atoms atoms have their own nuclei. Let's say here nuclei are indicated, and as we talk, nuclei have their own magnetic field, and those magnetic fields have their magnetic moment, their own direction. At their stationary state, they might have different directions and changing, let's say, tendency, but under the effect of magnetic field, those changing magnetic fields are aligned with the external magnet, as indicated here. We said that the nuclei with a lower magnetic energy are aligned with the magnetic field. Here, those that have lower energy are indicated, just to understand. The ones that have higher energy have the spin against the magnetic field. So this is the point that we have to understand how the magnetic field becomes, let's say, constant by the automagnetic field. And another oscillating magnetic field is formed around the studied compound, and the power, let's say, the oscillation changes, the magnetic field changes around that nucleus, increasing, decreasing, increasing and decreasing. So here, under the changing magnetic field, switch on and off conditions, those atoms being studied, hydrogen, for example, have its own, let's say, resonance, and those resonance are turned into the signals as indicated here. It has this kind of, let's say, changing action under the oscillating magnetic field here. And there we observe resonance under the changing, let's say, under the changing radio frequency. So those changes are turned into the frequency, and based on those frequencies and signals, we are able to identify the compounds that belong to different functional groups. And another point that we have to understand here is that This kind of changes are also, let's say, resulted from the shielding or deshielding effect of the electrons. If the electrons are closer or far from the nucleus, that might be observed in different functional groups like CH2 in alkanes or OH in water. Yeah, based on the electronegativity differences between the atoms that are linked with hydrogen, for example. The electron density of the hydrogen might differ, and that causes the resonance that could be observed under the effect of slightly differing radio frequencies. This is the point that determines the mechanism of the nuclear magnetic resonance under the magnetic field. Okay, here we can observe this kind of action that the frequency disappears. So this is the point that determines the NMR. Magnetic resonance imaging, a very similar technique, uses the relaxation of the spins of hydrogen atoms to obtain images of the human body. This is the point that we have to understand how the magnetic field can magnetic field of the atoms like hydrogen or carbon-13 are affected under the magnetic field, external magnetic field and oscillation. Okay, next. Here we can see that in their stationary phase, atoms, I mean the nuclei of the atoms have their magnetic fields change to different directions, and under the effect of the external magnetic field, we can have ordered spin of atoms. The nuclei that have lower energy are aligned with the external magnetic field, and the nuclei that have higher energy have reverse let's say, direction against the external magnetic field. And so the ones that have low energy that are aligned, as indicated in blue, that are aligned with the external magnetic field are named alpha spins, and those that have higher energy are named beta spins. Okay, again, hydrogen have strong signals, carbon-13 have signals that are detected, but they are low bonded. So the carbon-13 is the atom that gives us the signals. Carbon-12 are not detected in NMR. Fluorine-19 is very sensitive. Phosphorus-31 can also be detected, and it is important in biochemistry. Deuterium, again, it produces the signals, but it is used as solvent because these signals are not very strong. And broad peaks are obtained that belong to nitrogen. I mean, that belong to nitrogen. Again, carbon-13 is not abundant. It makes only 1.1% of the carbon in the nature. Besides carbon-13 and carbon-12, carbon-14 is also present in the nature, but its amount is very limited. It can be found in trace amounts only. Okay, so again, protein is identified in NMR, carbon-13 is identified, but not carbon-12. Carbon-12 is inactive. And the point we have to understand, another point we have to understand is that higher frequency leads to larger Hertz differences between signals. If we use 500 megahertz radio frequency in the NMR, so we might obtain these kind of signals, yeah. But if we use 750 megahertz radio frequency, so we can have quite different, quite good differences between the signals that we can really identify the belongings of these three peaks, yeah, and that they are different from these three, or by using 900 megahertz, we can obtain even better signals with more resolution in the gaps between the signals. Okay, so proton NMR spectrum of phenylalanine at 900 megahertz is given here. The expansion show the additional dispersion and spectral simplification that occurs as the magnetic field strength is increased from 500 to 900. Again, the higher the magnetic field, the more dispersed or separated the NMR spectrum becomes. The stronger magnet, the unit of which is Tesla, leads to the higher frequency, and the higher frequency leads to the larger hertz differences between signals, but ppm stays the same. Part per million units stay the same. We are going to talk what these 1, 2, 3, 4 to 10 and 12 stay for, and I think I can give an explanation here as well. These are about the differences in the radio frequency. These are the numbers that belong to part per million. Okay, I mean 0 point means the signals that gives that belongs to the reference compound tetramethylsilane, and in that case, for tetramethylsilane, 750 million hertz gives that signal. The resonance is observed at 750 million hertz. Yeah, let's say, and that point is taken as 0 point. Compared to 0 point, the radio frequency of the compound, for example, that has the signal at 5, means that at 5, that frequency is 750 million, 3,750 hertz. So the difference in the radio frequency that belong to 0 point and 5 point is very little, very little. Yeah, we can say compared to part per million ratio, so the difference between them is 3,750. But compared to the let's say real number, let's say they are also real number. I mean, excluding the part per million part, so we can see the difference between 0 and 5 is only 3,750 that belong to 750 million. Okay, this is the point that we have to understand. And stronger magnet leads to the higher resolution as well. Here we can see that at 16.4 Tesla, we can see the differences that cannot be identified if we use 7.0 Tesla. So the higher magnetic field or the higher radio frequency enable us to have higher resolution results in the NMR spectrum. And here we can see the kind of linkage between Tesla and megahertz. 1 Tesla is around, let's say, 40 megahertz, yeah, and 1.5 Tesla is around, let's say, 70 megahertz. And these tools are not used. Let's say, I mean, these units of Tesla and these units of radio frequency are not used to study the NMR spectrum. Here we saw that the NMR spectrum radio frequency that we use for the establishment of structure are between 900 and 500 and 900 megahertz. Okay, so these units are just to compare the link, just to see the relationship between Tesla and megahertz. Okay, here we can see that magnetic field unit is Tesla there. Strength of the static magnetic field of the NMR magnet. If the stronger magnet, it leads to the higher frequency, and here we can see higher. I mean, we can see the radio frequency. Yeah, you know, the frequency is the unit of the cycles of radio waves in 1 unit of time per second, for example. Yeah. So the higher magnetic field, the higher resonance frequency. Okay, and the chemical shift is also result. Chemical shifts are also resulted from the higher frequency. I mean, the one is resulted from, for example, smaller differences between the radio frequency of the reference compound and the radio frequency of the studied compound. Part mammalian is used to simplify the calculations, let's say. So by using part mammalian units, uh, we can better and more easily understand the differences in the radio frequency of the reference compound and the studied compounds. And here we can see the linkage between magnetic field strength, Tesla, and the frequency. 7 Tesla, for example, as indicated here, is around 300 megahertz. Yeah, this is 300 megahertz. And in 1 to 3 units, as indicated here, we use part per million. Yeah, and that part per million means that these 1 to 3 units are taken from 300 hertz, for example, or 500 hertz. Differences among them, not 700 megahertz. Okay. One point that we have to understand, we have to understand that part per million units do not change. They stay, let's say, stable. I mean, they do not change. If we use 300 and the signal is lower than 7, it has to be lower than 7. Or if we use 1500, around 2, slightly smaller than 2, and slightly smaller than 2 if we use 3000 hertz as well. I developed this figure by using ChatGPT. I didn't notice this discrepancy between 4.5 and 5, and here between 4 and 4.5. Okay, consider this is the error that does not stand for the right point. So part per million unit do not change as we use different, let's say, different radio frequencies. Here we can see that larger hertz differences between signals are result from the higher frequency, but ppm stays the same. Okay, this means that if we use 500 or 750 megahertz for the comparison of two different compounds like tetramethyl silane and ethane, yeah. So the differences between the signals between the signals of tetramethylsilane and the ethane stays the same. For example, around two at two different radio wave frequencies. Okay, there is another point that we have to understand that are termed upfield and downfield in NMR spectroscopy. Downfield is the left hand of the, let's say, chemical shifts, and upfields belong to the right hand. Uh, Upfield can be, let's say, between 0.0 and 4, and downfield can be, let's say, between 5 and all other parts between 5 and 12. Yeah, here it's written 6 and 12. It appears on the left side. I mean, the downfield de-shielded effect appears on the left side, and upfield appears on the right side. And shielding effect here, it is shielded and it's de-shielded. Shielding effect results from the distance of the electron, in our case, electron of the hydrogen, whether it means whether it's close or far from the nucleus of hydrogen. If it's closer to the nucleus of the hydrogen, so then we can expect higher electron density. Or if it's far from the nucleus of hydrogen, we can expect lower electron density. If electrons are closer, so then it can lead to the higher electron density. That higher electron density leads to the shielding effect. Okay, so that shielding effect results from the higher electron density. And that higher electron density comes from the closer distance, let's say, of the electron of hydrogen to its nucleus. Okay, it means, for example, in CH2 or CH3, the electron density of the carbon is higher compared to the electron density of hydrogen in aromatic compounds. Why? I will try to explain. Okay, the difference between electronegativity levels, levels of carbon and hydrogen is the same in alkyl protons or in aromatic compounds. But here, this carbon tries to cover the need of carbon to electrons from two hydrogen atoms. I mean, carbon tries to attract and fulfill its electron density with the electrons of two carbons. Okay? And these carbons that are located inside the aromatic cycle, which have the ratio of carbon and hydrogen 1 to 1, tries to cover its electron need to attract the electron from one hydrogen only. So based on that, this hydrogen has lower electron density compared to the hydrogen that has higher electron density that belongs to the methyl group or methylene groups. Okay, this is the point why some electrons have shielding effect and some do not have shielding effect. Okay, I hope you understand my point, and this can be a better explanation that these hydrogens have lower, let's say, electron density than these hydrogens because of the oxygen that has the chemical bond with the carbons that these two hydrogens belong to. I mean, here this carbon has a covalent bond with another carbon, and on this side as well. Or this carbon has a covalent bond with another carbon here. Okay, from this point of view, okay, the electron density of this carbon are attracted by the oxygen, and the electron density of this carbon is smaller than the electron density of this carbon. That is why this carbon tries to attract more electron density from these two carbon atoms. Okay, so the electron density of these carbon atoms is smaller than the electron density of these two. I mean, the electron density of these hydrogen atoms is smaller than the electron density of these hydrogen atoms. Okay, therefore, therefore, the signals that gives, I mean, the resonance and the signals uh, that belong to methyl groups are resulted from the smaller, let's say, radio frequency, not a bigger radio frequency. Okay, the radio frequency of these electrons. I mean, radio frequency of the radio wave is given to this hydrogen is smaller than this one, which means the energy it is absorbing is smaller than the energy that these hydrogen atoms are absorbing. I hope I made myself clear. So the shielding effect is the point that determines the location of the chemical shifts of different carbons. I mean, carbons or hydrogens that belong to different functional groups. Here we can see that aldehydes are located somewhere between 9 and 10. I mean, the hydrogen of the aldehyde groups belong to the location between 9 and 10, or in aromatic compounds between 6 and 7.5 or 8 and so on. Okay, again, let me remind that the difference between the radio waves of 0 point and 7 point is that at 0 point we can use, for example, 750 million hertz, yeah, 750 million hertz, or part per million we use, let's say, 0 hertz. And here at 7, we use 750 million plus 7 is multiplied by 750. Because in part per million, we use 750. Again, take a look at this point and try to understand my explanation given at this point again. Okay, so then it will be easier for you to understand what I mean. I am trying to do my best to explain what we need to understand in order to understand this 1, 2, 3, 4 up to 12 points. Okay, and in carboxylic acid, the chemical shifts are observed between 10 and 12. And these are the examples that we can see that in saturated hydrocarbons, the signals belonging to the hydrogen is located between 0 and 1.5, for example. Yeah, or in allylic compounds, the hydrogen belonging to the carbon that has a connection with the hydrogen that has the double bond with another carbon is located between 1.5 and 2.5. Or the hydrogen belongs to the carbon that has a halogen in the composition is located between 3 and 4. The chemical shift is located between 3 and 4. Okay, and this, for example, I mean, the hydrogen that belong to vinylic functional group is located between 5 and 6. In aromatic compounds, between 6.5 to 8, as we talked earlier, or between 6 to 7.5, as indicated in other sources. Okay, this is another good example. Here we can see that the the hydrogens that belongs to, for example, ethane or propane might have the chemical shifts between zero point 0.9 and 1.2. Or the hydrogen, two hydrogens that belong to carbon that has the bonds with other carbons might have the chemical shifts between 1.2 and 1.5. Okay, these are the pointers, and I'm not going to explain all of them. The point that we have to understand, again, that can explain the shielding effect and electron density, that the electron density of this hydrogen is higher, and the electron density of this hydrogen is smaller. The electron density is of these two electrons are closer to the carbon atom in this case than those belong to that carbon atom. So here higher frequency is required. So the chemical shift of this carbon is located between 6 and 8.5 or 8. Okay, and in this example we can understand all of these pointers I have been trying to explain to you. These three hydrogens are linked to the carbon, which has a chemical bond with another carbon, okay, with another carbon. And these three hydrogen atoms are linked to the carbon atom that is linked to the oxygen, okay? This is the point we have to understand. These three hydrogen atoms have higher electron density than these three hydrogen atoms that have lower electron density. Why lower electron density than these ones? Because this carbon has higher electronegativity than these hydrogen atoms. The electronegativity value of carbon is 2.5 and the hydrogen electronegativity level is 2.1. So these electrons that form a chemical bond between carbon and hydrogen are closer to the nucleus of the carbon atom. So these three atoms are attracted. I mean, these three electrons are attracted. These three electrons that belong to these hydrogen atoms are attracted by this carbon. Okay? But this attraction is less than this attraction. This carbon attracts these three electrons more than this carbon. Why? Because the electron density between this carbon and oxygen is closer or more attracted by this oxygen. That is why this carbon has a tendency to attract these three electrons with higher strength compared to this carbon. And this explains the shielding effect that results from the higher electron density of these hydrogen atoms than lower electron density of these hydrogen atoms. Therefore, okay, these three hydrogen atoms have the signals around 2 here, that is closer to tetramethylsilane, and these hydrogens have their signals between 3.5 and 4. Okay, because these signals or the frequency, I mean the signals require more frequency of radio waves that has higher energy because they have lower electron density, and as explained, as we go far from zero, we can see lower and lower electron density of the hydrogen atoms. I hope now you understand my points of view. Uh, Again, that in carboxylic acids, here we can see in carboxylic acids, this hydrogen's chemical shift is located between 10 and 12. And the shift of this hydrogen is between 9.5 and 10.5. In aromatic compounds, again, the chemical shift of this hydrogen is between 0.6.0 and 8.5. I hope you understand what I mean. If not, again, try to watch this video so then you can understand it better. Okay, I explained these points in the previous pages. Again, nuclear magnetic resonance is the method that studies the nuclear spin, uh, magnetic field interaction that absorbs various radio frequencies, yeah, based on the absorbance, yeah, which leads to the resonance. We can identify, again, based on the radio frequency that are absorbed and leads to the resonance, we can identify the hydrogen, for example, that belongs to different functional groups, that belongs to methyl group or OH group, or the methyl group that's linked to carbon-carbon double bonds, etc. Okay, this is the point how the NMR spectrum are obtained. Okay, we talked about the chemical shifts, and there is a term coupling in the next video lesson. In some examples, in exact examples, we will learn about the coupling and the integration, which belongs to the peak area. The peak area is proportional to the number of nuclei contributing to the signal. If some carbon atoms number is higher in one compound to the compared to the carbon that belongs to another functional groups. So the higher number of carbon or hydrogen compared to another one uh, makes a peak with a higher, let's say, peak area. Okay. NMR provides us with structural information, as we talked, and it also provides with quantitative data, and also we can learn about the molecular dynamics properties of the compounds. We will talk about this at the end of the video lesson. And as I explained it at the beginning of the video lesson, that NMR has this kind of tools inside it based on the energy that causes the resonance. We learn NMR spectroscopy. So the compounds are dissolved in either deuterated water or deuterated chloroform based on their uh, hydrophilicity or hydrophobicity. They are dissolved in one of them, located here in a sample tube, and around them there are radio frequency coils. They transmit radio frequencies, and there is receiver coils as well. So they transmit and receive after resonance some emission from the nuclei. So those emissions that are termed, let's say, free induction decay are obtained, and they are transformed into this kind of signals by using Fourier transformation, right? So then we can identify different hydrogen atoms in each NMR that belong to various functional groups. Okay, so by using this kind of radio frequency, changing radio frequency, or turning on and off mode, we can transmit and receive in the detectors different, let's say, emissions. Yeah, and we can observe free induction decay, which are further turned into this kind of signals, and then we are able to identify different atoms in the compounds. So here we can see those things in another figure. Samples are located here, and sweep calls are provided with to produce radio frequency, and by using radio frequency receiver and amplifier, we can obtain the emission. So those data are used to develop the signals which we use for the identification of the compounds. So far, more updated versions of NMR spectroscopy have been produced. One of them is COSY. COSY produces proton-proton coupling effect. It identifies scalar J coupling between protons through chemical bonds. And another type is termed HSQC NMR. It correlates protons with the carbons to which they are directly attached. So this is a kind of method that we can more effectively and more freely, more easily use for the establishment of chemical bonds. Establishment of functional groups based on the correlation between protons and carbons. And another one is noisy. It shows through space interaction between protons that are close in space, not through bonds. So it can tell us about the, let's say, about the properties that could link with the molecular dynamics properties of those compounds. So noisy is a kind of suitable method for polymers like peptides or proteins, but we have to highlight that as the molecular mass of the biopolymers increases, the effect of the noisy is not very suitable. So for peptides, noisy can be a kind of more appropriate technique to learn about the spatial proximity of the proton. And it helps to determine the 3D structure and stereochemistry related features as well. These are all that I wanted to deliver to you, and I hope you found this video lesson useful. And I kindly ask you to help us with your likes so then our video lessons can reach a wider audience. And I express my thanks to you for watching us. Have a good day and bye.